So we're on to now our next set of talks. In track one, we have Andrew Bolster. Some of you may know him, and he's discussing the tools and skills for data science newbie to understand complex production data structures. And then track one, we have Ciaran Conliffe on creating your own domain-specific language and the tools and challenges that he faces with it. So over to Ciaran.
Hello everyone, and welcome to Creating Your Own Domain-Specific Language for Fun and Profit. My name's Ciaran Conliffe, and I'm here today to talk to you about language and complexity. Complexity is a tricky thing in software engineering, which I think is a side effect of the way we're taught how to program. We're given these techniques, and then we're given simple examples to use them in, which is all well and good when you're just learning, but it trains people to expect simplicity. And then you get out of university, you go to the industry, and all of a sudden very complicated things are thrown at you and you're expected to understand them immediately. Things like this. This is the Goose Game. This was very popular back in the 18th and 19th century. It was one of the first board games printed in Europe with a custom board. And this presentation of it is extremely complicated. But it's also a great demonstration of the different ways that something can be complicated. In his 1986 paper, No Silver Bullet, Fred Brooks defined two different types of complexity. Essential complexity, which is how complicated a problem is in and of itself. In this case, the game is quite tricky. There's a load of special spaces, and if you land on them, weird things happen, and it's a lot to take in and learn. But also there's accidental complexity, which is the complexity that we add to a problem through how we explain it and how we implement it. The explanation here is a big block of cursive that's quite hard to read, and the implementation is this whole non-linear arrangement of circular squares and muddy illustrations. It all adds up into something very complicated and very hard to understand. What I'm here to talk to you about today is a problem that I had to deal with 10 years ago that was extremely complicated, and how we used a domain-specific language to help strip away all the layers of accidental complexity so we could deal with the real underlying problem. Since I work for Liberty IT, it shouldn't be that surprising that the problem involves insurance. More specifically, it involves the fundamental difference between insurance here and insurance in America, which is driven by Americans' love of freedom of choice. Over here, insurance is fairly simple and straightforward. Your home insurance is how much does your home worth, how much your content's worth, here's your quote. Car insurance, what type of car do you have, how old is it, what's your driving history, do you want third party or fully comp? In America, it's much more customizable, and there's all different ways you can tune your insurance. If you're insuring your car, you can say, I don't want to insure my windshield. I do want to insure my windshield, but if it's damaged, I'll pay the first 150 quid. I do want to insure my windshield, but only up to $1,000, and then anything beyond that I'll pay myself. Multiply that by all the other different possible coverages, which is what we call them, such as uninsured motorist coverage, where an uninsured motorist runs into you, or accidental coverage or collision, and you get a very complicated problem. The second layer of essential complexity of the problem, though, is that America is composed of 50 different states, each with different laws and regulations around insurance, and those can vary greatly. Texas is completely different from Massachusetts. That speaks to the fact that all those states have different cultures, which means that your marketing teams have different strategies that they want to apply. So you might have exactly the same coverage in two different states, but with a different name because they decided that one would appeal more. The third layer of complexity is that this isn't static. All of these change over time. Obviously, your marketing team want to do different things as time goes on, but also the laws and regulations are constantly in flux. At one stage, I was coming into work every morning and checking the Florida local news to see whether I needed to push a particular change to production, because they had allowed their law that you needed to have insurance to drive lapse. And they didn't have time to get through new law in time. So there was a period where you didn't need insurance to drive, and it was going to become law again, but we didn't know when. And as soon as they actually scheduled the law to go through, I was able to push my change to production to put that back into force. That's where I come into the problem, by the way, which is that I was responsible for an application that customers could use to service their policies online. So they could register their policies, they could pay simple bills, file simple claims, and view what coverages and options they had on their particular policy. This is not that application, because it's a lot easier for me to clear this stuff with our legal and comms department if it's an obviously fictional example. So this is a mock-up, but it is straightforward, analogous to how we would have presented home insurance in that application. Just for the rest of this, I will be talking about space stations instead. This is actually the simplest possible iteration of this problem, because we're just reading in what's on your policy and showing it to you. And that would seem to be fairly straightforward, but this one screen was responsible for 75% of all production defects in that application. The reason for that is, A, it's a very complex problem, but B, this is how our requirements were set out. Because I said this was 10 years ago. This was the era of waterfall, where you had these gigantic requirements documents. And so we had about 100 of these packed into a Word document about how different coverages might be displayed in the app. This is really hard to parse. It's hard to translate into programming code. It's hard to test it and figure out what the different cases are. And what you can't tell from this is that it's actually missing key information. For example, that Martian oxygen coverage, we need to know that in 3 pages time for a completely different rule. So we would have code in here to record that, but that's not expressed in the requirement. Luckily for us, the whole internet thing kind of caught on, and it became more important as a tool of communication with the customers. And that meant that there was a lot of focus on the application, and we wanted to scale it up. We wanted to make it a better user experience, make it easier to customize, and that gave us the opportunity to rewrite this particular page and change how we handle these requirements. And my architect at the time said, why don't we use a domain-specific language for that? And I said, what's a domain-specific language? What is a domain-specific language? Well, it's a language that is specifically designed for solving problems in a domain. Simple. This is as opposed to a general purpose language. Most programming languages are general purpose, so C or Java are designed to solve problems across all possible domains. There are 3 main categories of domain-specific languages. There's markup languages, like HTML, which is designed for the domain of how do you display a web page. There are domain-specific programming languages. My favorite example is Twine, which is specifically designed for producing interactive fiction games. And then there are domain-specific modeling languages. They're a bit different because they don't directly feed into computers. They're more designed for helping you to specify problems at a high level. And as a result, they're usually a lot more custom, and building your own is usually what you would do in our type of situation. So it seemed like a good fit to us. It seemed like it would solve our problems. However, we did have to sell this to the business side of things. This was a technical solution to a business problem, which is always a tricky sell. So we flew over to this lovely building in Portsmouth, New Hampshire, and sat down with them and went through the possible benefits. We showed them all the defects that could be tracked back to that particular screen. We showed them our projections for how long it would take us to code and test the screen with the current state of the requirements. And they were convinced. They said, like, yeah, no, you've sold us on this, but we'd like to do a little time-boxed experiment to prove out the value of this. So myself and 2 of our more technically minded business people, Andrew and Nama, who were brilliant, and I was really lucky to have them at the time, we went into a room and sat down and said, okay, by the end of this, we're going to come out with an approach for documenting our requirements in an unambiguous way. So the first thing we did was go to what we currently had and start diagramming it out. So on this particular example, what's in red is the criteria for taking particular actions, and what's in blue is the actions that we take. Now, a few things become apparent as soon as you do this. The first of these is that this is an awful way to document this, and it shows the shortfalls of human language for documenting it, because all the red and blue are completely mixed together, and it's not necessarily clear which relates to the other. The other thing is that there are loads of possible outcomes, there are loads of possible criteria, there are actually multiple rules bundled up here together that all relate to the same thing. So we started pulling those out and creating atomic clauses, which were the words of our new language. And this is what we pulled out of that particular requirement, and we were able to collapse things together like, okay, there's a few different things that relate to specific planets. So the planet that you're at is a clause that has a variable into it, which is the specific planet, that sort of a thing. And we also documented the actions, and we added in the actions that we knew weren't documented. And we repeated this for a whole bunch of these different requirements, and we were able to go, okay, let's find some commonalities, let's start collapsing things together a bit more. At that stage we had, okay, here's how we can express this, but how do we document it? What's the best way to communicate it? We could have done another big document out or a big wiki page or something, but that would still have been fairly indecipherable. So we decided to go with the business solution, which is a spreadsheet. And I mean, spreadsheets get a bad rap, but in this case it was good. It allowed us to put some structure on the way that this was expressed. So in this particular example, each row is a single rule that will have a single output, and each of these columns is a criteria. And we have it set so that a criteria is, for example, planet, and then each cell is a variable that that rule feeds into that criteria. And one thing with this is we have to be careful that these criteria don't overlap. So you might notice at the start we have a rule that it applies to orbital stations, and then every rule after that says this rule doesn't apply to orbital stations, so that we don't get confused. We also documented the actions that we would take based on those rules. And that includes the functional ones like the label we're showing or the format we're displaying the amount in. But it also includes things like the display order and so on, because we needed to document that somewhere, and this is as good a place as any to do it. So we had this format for documenting these unambiguously, and the business were delighted with it. They thought the experiment was a success. They were happy to go forward with it. We had other plans. We wanted to take this a bit further. So you might notice the second row there has what looks like pseudocode for each of those rules. And that relates into the other big cause of errors on that original page, which was programmers having to take these rules and put them into code. Now that we had these stated unambiguously, the next logical step was to automate turning them into code. So we chose to do this through a rules engine, and we chose Drools as our rules engine. It was a good fit for us because it's Java-based, and this was a big Java project. It was also handy that Drools stores its rules as simple text files, so we could have a Java class that just fed in our spreadsheet and knew this column turns into this line in Drools, and I just dropped the variable into it. In this particular case, then, the way this acts is the code that's using the engine has a request parameters object and a list of coverages, and it feeds them through the rules, and the rules say, okay, set these extra fields on the coverages and then add it to the list that we pass to the client. And then the client is able to read these fields and use that to drive the display. And each role is named so that it maps back to the specific spreadsheet row. So if there's an issue, then we can trace it back and go, okay, that's where that exact problem is in our requirements. We did still have to test all this because automation is a fantastic way to more efficiently make mistakes. And so we decided to use FIT for that, which is the framework for integrated tests. It's not really used that much these days. FitNess is sort of its successor. But it was what we decided to go with. The big advantage was that the actual input test cases is these big HTML tables. So it was fairly easy to put that in front of the business and get them to verify it and build out tables using HTML editor. The way it works is it has a piece of code called a fixture that reads this in and then feeds that into your rules. that was actually a bit of a pain point for us because that fixture was quite complicated and we wound up having to test it. And whenever you're getting defects in your testing code, that's a sign that things have gone wrong. But the other problem with this was actually really good for our initial release. When we had a big bang, we had a huge number of these to cover. But as time went on, it proved a bit brittle, and updating it became a bit of a pain. But what did happen when all of this came together? Well, the basic result was that all the defects from that page that had been 75% of all our production defects dropped to almost zero. And that's not just the defects that came in from that accidental complexity where people had made errors in terms of taking the requirements and turning them into code or transcribing the requirements, but also the logical errors. Because it turned out that the business were now able to see much more clearly what their rules were and what their requirements were. And they were able to make more intelligent decisions about what they were going to do and not be caught by unintended consequences of changes. So that was really good. The only real problem was that we became victims of our own success because people would come onto the project and go, why do you have this whole complicated process for this page when you don't get any defects on it? And it's like, yeah, no, okay, so what do you think we would do? And then if people actually had good ideas for changes to it, we just took their ideas and rolled them into it. But usually once people saw the underlying essential complexity, they started to understand why we needed to do this. So it's the future now. We live in 2020, 10 years later. How would I do this if I had to do this again today? Well, number one is like lessons I've learned from this. Separating out, I mentioned like we had issues with the testing, and the root cause of that, I think, is that we were separating out the requirements and the tests, which is a consequence of using waterfall, but luckily we're all agile now, so we're not really tied into that. So I would find some way to bind those together a bit more. We were kind of constrained by the data as well. Like we were only one of multiple applications that used the same back-end services to handle this data, and a more modern pattern like a system of engagement would help us to separate that out. And the other thing is the actual underlying architecture. So again, this was 10 years ago. This was a SOA project. I don't know if anyone remembers SOA, but it was the first attempt at doing microservices, and it was really just monoliths with an API on the front. And I think modern functional architectures and serverless architectures would actually be a really good fit for this in terms of being able to deal with each rule on a more atomic level. So at a very early, like just with a quick amount of thought, here's kind of how I would do this today. I'd probably still go with spreadsheets for the requirements capture. It worked fairly well. Again, like you're getting the business to put this in is a great way to get data in a coherent format from non-technical people. And there are much nicer tools in terms of collaboratively using spreadsheets and tracking the history of them, which was one big problem for us. Source control at the time did not like Excel spreadsheets, so it got kind of tricky. In terms of the testing, I'd probably go with Cucumber. I think like BDD is actually very closely aligned to what we were doing in terms of building out this language, and Gherkin is really just a way of creating a domain-specific language for your testing. So, and I think it'd be fairly easy to automate having your requirements go over into Gherkin scripts and sort of feed in variables. So again, like you wouldn't have to maintain them entirely separately. For the rules engine, Drools is still around. JBoss maintain it now. It's quite nice. It's got like a graphical front end to it now, so you can see your rules as tables and map them out and so on. But other rules engines are available, and as I said, I think doing this in a serverless way would probably give you a lot more options in terms of coding it yourself as opposed to relying on a rules engine. So that'd be fun. So it'd be good to dig into. So what have we learned from this? Well, if you're faced with complicated requirements that are really difficult to understand, break them apart and build them back up again in your own language. And that way you can state them unambiguously. Once you have things stated unambiguously, then automate turning those into code so that you're taking out any human factors in the error. But still make sure that you're testing everything and that you're not leaving yourself open to having mistakes go out there without you being in the middle to intervene. Lastly, remember that even though you're automating this, even though you're creating this magical language for it, people are still going to have to deal with this. You need to make sure that this is something that people can comprehend and work with. Going back to the Florida example, I had, in that particular case, I didn't want to be in on the specific date when this change went live, but luckily we'd had added rules clauses that let you say this particular rule will become effective on this particular date. So that was all taken care of, and I could push my change as soon as I find out rather than waiting until the day. So hopefully this will all prove useful to you, and thank you very much.
Another fantastic talk from Ciaran, another reliable speaker there.